Welcome to today's lecture. Today we are going to continue from where we had left in the previous lecture.
Now method number 6, we are going to study the introduction of springs for bringing down unwanted vibrations. This remedial measure is effective for situations where the frequency ratio is greater than 1. When springs are fitted below the foundation, the natural frequency of the foundation machine system reduces, so the frequency ratio increases. So as shown in the amplification factor versus frequency ratio plot, the amplification factor and hence the vibrations reduce. This is especially useful when the foundation block is resting on very stiff soil or rock, because in such situations, as we would see later in this lecture, the transmissibility of vibrations is very high. So the introduction of springs below the foundation, like it's shown here, definitely reduces the stiffness and hence it brings down the amplification factor and the transmissibility of the vibrations in the surroundings. Alternatively, springs can be introduced just below the machine itself rather than introducing them below the foundation block. So this is also a viable alternative. However, in such situations, although the overall vibrations would reduce, but the vibrations of the machine itself might increase, and this may increase the wear and tear in the machine. In certain situations, the performance of the machine might also be compromised. So it's always advisable to consult the manufacturer before this measure. Next, we are going to discuss the remedial measure of trench barriers. The basic principle here is to cut off the stress waves generated by the machine. Unlike the previous methods, this does not involve any change in the stiffness or the mass of the machine foundation system. Therefore, it is effective for the foundation system of wide variety of machines. and it is specially preferred and effective for the impact type machines such as forge hammers. Let's say this is the foundation block in plan with the machine resting at the top as shown here. Operation of the machine shall generate stress waves all around as shown here. So these can travel long distances through the soil. So this remedial measure involves creating a trench all around the foundation block as shown here. The trench can be seen in the elevation also as is shown here now. The depth of the barrier should be large enough so as to obstruct the waves. Otherwise, large waves they can cross small trench barriers without being affected. Next, we are going to discuss the use of highly damped or highly elastic materials or their combinations. We shall discuss three materials in this category: cork, felt and rubber. Cork and felt, they have very large damping ratios, so they suppress the vibrations. As far as rubber is concerned, its main effect is by altering the stiffness, so it's useful for the situations where the frequency ratio is greater than 1, but it has some inherent damping also, though small as compared to cork and felt. So the use of cork and felt for vibration isolation is independent of the frequency ratio. But for rubber, it's applicable when the frequency ratio is greater than 1. So essentially, rubber acts as spring. But cork and felt, they essentially reduce the amplification factor curve by means of increase of damping. Let us first study cork. Cork is especially effective in providing isolation against shocks, rattling sounds, in addition to general vibrations. Its density is usually in the range of 2 to 4 grams per cc, and commercially it's available in sheet form. So we use it for vibration suppression as paddings in sheet forms. It is best to use felt sheets as paddings in between the machine and the foundation block at the points of anchorage as is shown here. But we need to exercise certain precautions for cork to be effective. Number one, it should not come in contact with water or oil. Secondly, it is effective only when it's confined against lateral expansion. otherwise it will disintegrate very fast. To enforce this, we need to provide metallic blockages all around as shown here. Let us now study felt. Felt is a fibrous material made from natural or synthetic fibers. Similar to cork, this can also be inserted as sheets at the anchorage locations in between the machine and the foundation block. So it also serves like a packing. It has typical compressive strength around 8 megapascals and a Young's modulus of close to around 80 megapascals. The only precaution we need to undertake for its effectiveness and longevity is that we should make sure that it does not come in contact with water or oil. As previously stated, rubber is effective by means of its spring action. So it's applicable for the situations where the frequency ratio is greater than 1. Let us see some of the prerequisites or precautions. So number 1, when we are using rubber, we should allow lateral expansion. So this is in contrast to cork, where lateral expansion should not be allowed. So rubber is effective only if there is no blockage. Then, just like the case of the cork and felt, we should avoid its contact with water or oil or any chemicals. Nowadays, water and oil resistant variants are also available in the market. Commercially, rubber is available in various grades, and the grades of rubber are classified in terms of shore hardness. So when we go to buy rubber, we need to specify its shore hardness in terms of degrees. So there are rubbers available in shore hardness 40 degree, 45 degree, 50 degrees, etc. So all these different grades, they have varying elastic properties. So here we are just reproducing a table from the book which lists the basic properties of rubber of different shore hardness. For vibration isolation, rubber is usually used in form of blocks. Let's consider a block of rubber of width B, length L and thickness in the vertical direction H, and let's say it's under the action of stress in the vertical direction. So here in case of rubber, both the Young's modulus of elasticity and the bulk modulus of elasticity play important role. In order to determine the stiffness of a block of rubber, we need to define a parameter called as area ratio. It's basically the ratio of the area to the product of the perimeter and the thickness. So for this block of the rubber, we can derive an expression for the area ratio as shown here, that is LB divided by 2 L plus B H. Then we can write an expression for the overall stiffness of this block in terms of E, the Young's modulus of elasticity, and B, the bulk modulus. In this expression, area ratio also comes into picture. The constant alpha here depends on the particular grade of rubber. If you just see the table of the properties of rubber, you will find that the bulk modulus is very large as compared to Young's modulus. So if we ignore the term involving bulk modulus, then we can write this expression, an approximate one, for the stiffness of this rubber block. Also, if we ignore area ratio, then we can write a very simplified expression, EA by H, which is just the equivalent of EA by L for elastic members. For the last expression, EA by H, the inherent assumption is that the thickness H is very large as compared to the lateral dimensions. Let us take an example block of rubber.
the length and the width, let they be 100 mm, and we keep the height h as a variable factor, and we'll do computations for different values of h. Let us consider grade of rubber as shore hardness 55 degrees, and for this shore hardness the various properties of rubber like the value of G, E, P and alpha are as shown here. So here G is basically the shear modulus, B you already understand is the bulk modulus, and E is the Young's modulus of elasticity. Alpha is the constant of this particular grade of rubber. We shall do calculations in tabular form as shown here. So we shall basically be calculating the overall stiffness of this block of rubber for various values of h, and we'll use three relationships. First, we'll calculate the stiffness as per the exact relationship, taking into consideration the bulk modulus of elasticity as well as the constants alpha and AR. Next, we will make approximation. We will simply exclude or ignore the bulk modulus B. Once we do this calculation, we'll also find out the error with respect to the exact answer. After this, we'll use the most approximate relation EA by H, and for this case also we will determine how much is the error with respect to the exact calculation. So here in one column we are writing the value, and in the adjoining column we are writing the error, keeping the exact value as the reference. So it is a homework for you. You do these calculations for these three values of h. So use the exact expression and also the two approximations and find the error and the values. You may use Newton per mm as the unit. Now, last section of today's lecture is the concept of transmissibility. This is also something very much relevant to the problem of vibration isolation. To understand transmissibility, let us consider two scenarios. In the first scenario, we consider the machine supported on block foundation, which is in turn resting on the soil. So we are considering the mass associated with the system, the spring and the damper. And let's assume that the machine is generating force Fm, which for simplicity we assume is acting in the vertical direction. Let Ft be the force transmitted into the medium below the foundation. For such scenario, transmissibility is defined as the ratio of the transmitted force to the generated force. Now let us consider a second scenario. So here we are not dealing with a machine foundation, but let's say we have a sensitive equipment which is resting on a support system which is connected to the ground. We are modeling the support system as a combination of spring and damper. Let's say the ground is undergoing vibrations. Here we assume vertical vibrations and the acceleration is ag, and because of the vibration of the ground, an acceleration am is induced in the sensitive equipment. Now in this scenario, the transmissibility is defined as ratio of the induced acceleration to the source acceleration of the ground. In both the scenarios, the expression for transmissibility is same, and you very well know the expression having learned it in your structural dynamics course. So this expression depends on the frequency ratio and the damping ratio. If we ignore damping, then we get a very simplified expression, simply 1 divided by 1 minus r square. So we have to take the absolute of this, because this might otherwise come as negative in cases where r is greater than 1. Let us try to plot this equation, and we have on the vertical axis transmissibility, and on the x-axis we have the frequency ratio r. So here we have a critical point at r equal to 1 and root 2. The plot is similar to that of the amplification factor studied earlier. So it reaches a maximum value at r equal to 1 and then goes down. This is a typical curve for damping ratio in the range, say 5 to 10%. If we want to plot the variation for zero damping ratio, then this is how we get. So what we find is that transmissibility is infinite for frequency ratio 1, that is at the resonance. You can also note that for frequency ratios less than under root 2, the transmissibility is always greater than 1, that is more than 100%. And for the values of R greater than root 2, it's always less than 1 or less than 100%. So what we find is that in the case of very high frequency machines where R may be greater than root 2, transmissibility shall always be less than 1, that is less than 100%. But for values of R less than root 2, transmissibility will always be more than 100%, and this is something undesirable. If we consider rigid ground, that is, if our foundation is resting on rock or concrete, then assuming that the stiffness is infinite, for that particular situation, the transmissibility shall come out to be 100%. Our transmissibility of 100% means that 100% of the force generated by the machine is being transmitted to the surroundings. So this is also an undesirable situation. So we'll study in the next lecture how we can play with transmissibility and how we can do correction so as to minimize the forces transmitted to the surroundings and so as to enable vibration isolation to maximum extent. So thank you very much. If you have any questions, you can discuss them during our interaction in the MST.